In this one, we're going to take a look at quadratics in a general sense and then how we can modify them by applying some transformations. So this is first going to start with the concept that when we have a quadratic and we have our formula ax squared plus bx plus c, the a value is the only one that's important. It has to be something that's not 0. The base value of it's 1. B and c, we can, if we disregard them, we can look at just a nice simple parabola and a nice simple quadratic, which is just x squared. So if you have y equals x squared, that quadratic function is a nice simple function that will give us a baseline graph that we can use to describe changes that happen as we change the formula up a bit. So here we have a table of values for this graph. I just went from -3 to +3. So each time, all it is the x value squared. -3 squared is 9, -2 squared is 4, -1 squared is 1, and so on. And then I plotted those out here on a grid. And so you see we have our nice parabola. So that's kind of our baseline parabola. Vertex is at 0, 0. It opens up. The domain is x belonging to the real numbers. The range is y belonging to the real numbers, such that y is greater than 0. Greater than or equal to 0. So that's kind of our baseline that we're going to be dealing with for the next couple of lessons and most of this unit. And then as we move into the next unit, we'll look at some other variations on the quadratic function. But here we're going to look at this. So this is going to be our baseline function all the time. Start at 0, 0 kind of as our vertex. That's our key point. It opens up, and then our domain and range are both x belong to the real numbers, the only thing with the restriction on the y being greater than 0. So that's our baseline. From there, we can look at some transformations. So one of the ways we can transform it is by just shifting it around or changing its shape. So in this one, we're going to consider y equals ax squared. So we're just going to be affecting the a value on the equation. And when we change the a value, there's 3 key transformations that can happen based on what the value of a is. The first one, if a is positive, then we just have, and we don't change, and we leave the value as 1. So here, going back up to this is technically 1x squared, right? We have 1x squared there. So if we just switch the sign on the a, anytime a is a negative value, it's going to open down. As the positive values will always open upwards. If a is a negative value, it's going to open downwards. It'll be the same graph, same shape. Just take this and flip it. It's going to mirror itself, flipping around the x-axis. So that's anytime we have a negative value, all you're going to do is take that graph, flip it upside down. Now, that's dealing with the positive negative portion of the a value. If we just look at the number, disregarding a negative sign or positive sign in front of it, and just look at the actual numerical value of a, it's called the absolute value, then if a is greater than 1, it's going to stretch the graph out. And so we have our baseline graph here in blue. There's our y equals x squared. And then it's going to stretch it out. And by stretching it out, it's getting narrower. And what's happening is, and you can take a piece of string or a shoelace and kind of illustrate this. And if you kind of hold it here at the vertex and you start pulling on these blue lines and you start pulling them up, what's going to happen is they're going to want to, as you pull higher up, they're going to want to come together and narrow out. So as you pull them up, they're going to narrow, and thus our graph is stretching and getting narrower. The opposite of that is if we, again, just look at the number itself, don't worry about the negative sign, but if a is less than 1, so between 0 and 1, what's going to happen is that the graph is going to widen out, and so that means we're compressing it. So if we were to take that stretch and do the opposite and kind of push this down, what's going to happen is the graph's going to end up getting wider to keep that parabolic shape. It's not going to get all wonky and wiggly. If we're always keeping that parabolic shape, then the graph has to get wider to accommodate that extra amount of material that's coming down as we push down. So if a is greater than 1, it stretches. If a is less than 1, it widens. And both of these could flip. So if I had a negative value here, like -2, then the graph would be the same thing, and it would just be narrower but upside down. So we're disregarding the negative part makes it flip, and then a secondary thing is to look at one of these. So if it's negative, it could do this on either one of these as well, and we'll see that as we look at examples with this. So if we continue, we're going to just do a graph of the following, and we'll look at this concept of the stretch, and I'll see if I can fit this all in. There we go. So we're going to graph each of these. So here we have a grid made out 0 to 16, just so I can show a few points. And then we went with the 4, so that's the base graph. So 1 squared, 2 squared, 3 squared, and 4 squared. And multiplying by 2, so we're going to take that value, and if we just make a quick little table here, I'm just going to do the positive numbers, but I'll make a quick little t-chart. So this is x, and then y for the standard graph. So we have 0, 1, 2, 3, and 4. And each time we're just, in the basic graph, we're just squaring it. So this is x squared. Sorry. So then x squared is just 0, 1, 4, 9, 16. Now, in this case, we should be stretching this graph, so it should be getting narrower. And we'll see that because we're stretching it by 2. So we take each of these squared numbers, and we got y equals 2x squared. And we have our x and y, and 0, 1, 2, 3, 4 again. So we have the x squared, and we're going to double it. So 0 doubled is 0, 1 doubled is 2, 4 doubled is 8, 9 doubled is 18, and 16 doubled is 32. This 2 in front just doubled all the values. So it kind of goes up twice as fast. So we take a quick way to do this without having to make the table is we look at the 2 and we take each of these points and we double them. So 0 stays the same, double 1 for 2, double 2, double the 4 for 8. And then if we double the 9, that's 18, so that's going to be 16, 18 would be about right here. So it's kind of off the graph, but I'm just going to put it there anyways just to illustrate it. Same idea on the other side. They're symmetrical graphs, so we can just double each of these points and quickly plot them. It would be right there. And if I connect those dots, and these aren't straight lines connecting the dots, they are curved lines. So try and give it a little bit of a curve to it. It takes a little bit of practice. I'm not the best at drawing, so be aware of that. But there you have our graph stretched by 2. Each point is going up twice as fast. So here it goes up by 1, so instead it goes up by 2. Originally it went up by 4, so it went up by 8. So everything's going up twice as fast in this new case here. So using that same idea, let's use that to graph this one. And I'm going to do an intermediary graph. So each point is going to do two things in this one because we have a negative sign. So the negative sign is going to make everything flip to the opposite side. So I'm just going to put some temporary points here. So I'm going to just take this and mirror it below. So there's going to be a point here, here. This would be at -4. This one would be at -8. Or sorry, -9. So it's down here. Sorry, and then -9 on the 3, -4. So there would be a really kind of, I'll do it lightly here. That would be the flipped graph. So there's the negative of x squared, but it's -1/2. So we've dealt with the negative, now we'll deal with the 1/2. So every point should be going up half as fast. So we just half all our points. So instead of 1, we actually have negative 1/2. Instead of negative 1 here, negative 1/2. Negative 4, so that's half of that's negative 2. Negative 9, half of that is negative 4.5. So I'm going to put these a little bit bigger, a little bit bolder. And now I'll connect those dots. And actually the negative 4 is going to end up being negative 8 because 4 squared is 16. That one's a little bit off. Curve that a little bit more. There we go. So there, and I'll get rid of that intermediary. I don't need it, that's why I did it light. We have the graph that's been flipped because of the negative sign, and it's compressed, so it's a little bit wider because of the 1/2. So that's what you can do to quickly graph those, is you can just draw a standard graph and then do those modifications based on the standard graph. And it makes it pretty easy and quick to do them. So now you just have to know the standard graph, and it's always going to just be 1, 0, 1, 4, 9, 16, 25, 36, so on and so forth, and then it mirrors itself on the opposite side. Sometimes you're going to need to figure out that stretch or compression factor, so you're going to have to find the A value. So we work with that base of y equals ax squared, and you can find that A as long as you have some point. So if you're given a graph, you just have to pick a point off the graph. If you're given a point, like in the example here, you just plug that point in. So if you're given a graph, you could do the same as what we're about to do. You just have to pick the point yourself. Don't pick the vertex, by the way, because notice both of these graphs have the same vertex, but they have different A values. Just pick any other point, doesn't matter which, as long as it's a point on the graph. So here, all we got to do is realize that when we're given a point, remember points are always listed as x comma y. So this is an x value, this is a y value. Well, our formula has an x and a y value, and we're trying to find A. If we just replace in y equals ax squared, we replace y with the y value, 4, leave the A, because it's what we're looking for, replace the x with a negative 6, and then that's squared. We can now solve that. Notice, I put the negative 6 in brackets. Don't write this, okay? Don't write 4 minus 6 squared. That's wrong. That means square the 6 and then subtract it from A. This means square negative 6. This is wrong, okay? You need to put the x, put your values in brackets when you have those exponents there. It's usually good practice in general to put them in brackets when there's other things going on. You can put the y here in brackets, but there's nothing else going on that side, so it's just going to be a 4 anyways. But if there's other things going on, good practice, put them in brackets. It'll affect things with the negative signs. So we do this one out here by doing the exponents first. So we're just going to square negative 6. That's going to give us 36. So I'm just going to flip it over here so it's 36a, because we usually write things like that. Now we just got to solve for a by dividing both sides by 36. And we're left with, oh my gosh, a fraction. And I know a lot of people hate fractions. I love fractions. They look so much better than a whole bunch of decimal points. But we can simplify this. 9 goes into 36 4 times. So that means 4 goes into 36 9 times. So these can both be divided by 4. Divide both by 4. Divide top and bottom by 4. And what we're going to end up with is 1 over 9 equals A. Now again, I don't like fractions. I want a decimal. And I'm just going to do 4 divided by 36. And what you're going to end up with is like 1.111111 repeating forever. And then that's not the exact same graph. And it'll cause slight fluctuations depending on what you're doing. Could cause an error. Simple errors like that in real world calculations could be the difference between a building standing and falling, a rocket ship hitting Mars or veering off and heading out into the middle of the universe with no actual target. So sometimes fractions are better because they give us exact numbers. So anyways, we have our a value, we found that, and now we actually have the equation too. So the equation for the quadratic that has a point, with a here, we just have y equals 1 over 9x squared. And that would be the corresponding equation.